In section 1.4, we explore how we really come up with the idea of derivatives. We compare slopes of tangent lines to slopes of secant lines, and then we kind of do that by working through what's called the tangent and velocity problems. A lot of times, our examples in calculus are going to be related to physics problems. We can use calculus to help us answer some physics problems. So I first want to take a look at these two parabolas that I have graphed or have constructed two different lines that intersect with these parabolas. The first, notice I just have a line that intersects the parabola at one point. So we call this a tangent line. And again, pause the video as often as you need to construct these images. Over here, where a line crosses a curve at two places, we call this a secant line. And one will help us sort of come up with a way to find the other. If you notice here, I kind of constructed very specific points of 3, 6. Over here I have 3, 6, and then I have negative 2, 1. Right now I'm just going to call this point P. I'm going to call this point P, and then this will be point Q. The actual ordered pairs, they're not necessary. They're just values if we need to refer to them. But ultimately, our goal is to find the equation of this tangent line. So because I generated this on my calculator, this was given to me. By the end of this section, we're going to figure out a way to figure out how the calculator came up with that. So our very first goal here addresses the tangent problem. We want to try to find the equation of a tangent line T to a curve with equation y equals f of x, so tangent lines are always just going to be linear, at a given point P. So this tangent line right here is T. And again, the calculator gave me the equation. We're going to figure out how that was possible, how the calculator came up with that. So in order to find the equation of any line, and in this case a tangent line, we need the slope of the tangent line. We have the point where the line is tangent to the curve, but we need the slope. But with only one point, how do we do that? Well, we kind of generate, or we kind of move closer to it by using what we know so far by looking at the secant line. So right now, again, with these 2 points, point P, I'm just going to call this A comma f of a. So ignore the fact that it's a 3, 6 as a specific point. I'm just saying any point P on a curve, I could just use, we're going to use A and f of a, and you're going to see why, because with Q, I'm going to use x and f of x. So if I wanted to find the slope of line PQ, I'm going to use just y2 minus y1. So I'm going to use f of x minus f of a. And yes, technically we can go in any order here, but I want to specifically go in this order. And then x2 minus x1, so I'm going to have x minus a. So we could write it like this, or we could just use the lowercase m and then call that, kind of abbreviate down here, little subscript, the slope of the secant line. So to find a slope of a secant line, it's just a line that passes through 2 points. This is just our y2 minus y1 up top and x2 minus x1 in the bottom. And this is, it looks a little different, but it is connected to the difference quotient, those examples that you guys were working on in sections 1.1 and 1.3. So we're going to use this to help us approximate. We want to find an approximation using a secant line by choosing another point Q. So here I just have y equals x squared. I want to just pick another point P. And again, I'm not assigning specific values here. But in order to find the equation of this tangent line, I'm going to draw this in here. We're going to first create secant lines. And I don't want to go too far away with my Q. So starting over here at Q1 isn't going to be helpful. I do want to move it at least to the same side, because over here, if I drew in any kind of a line over to here, I'll show you, this is going to be too drastically different. So notice the slopes of these two lines are very far apart. They're definitely different. So I want to move Q closer to P. So if I started maybe over here, I would pick a different point Q, and I would draw in that line and determine the slope of this secant line. And we're going to do a series of these. So if I were to draw a secant line in, definitely this purple line has a slope that's a lot closer to the red line than the original green line. And I could still move closer yet. So let's say I wanted to go very close. So we just keep picking a series of points until we get very close. I'm just going to call this be Q3, 4, so we call this Q5 here. And if I were to draw in that secant line, it would be even closer to the slope of the red line than the purple line was. So this is how we're going to sort of explain how the slope of the secant line can help us find the slope of the tangent line. As point Q approaches P, so that's what this notation means, as point Q approaches P, the slope of the secant line approaches the slope of the tangent line. We're going to go back to the slope of the secant line formula, which was just that f of x minus f of a over x minus a. And the slope of the tangent line is going to equal this, but to show that approaching aspect, we put a limit notation in front of it. And this happens because this is going to be my first x value. Let's say x1 is here. Over here I have x2, then I have x3. And remember, point P was a comma f of a. So as all my x values get closer to a, then the slope of the secant line approaches the slope of the tangent line. So as x approaches a. So this is our definition of the slope of a tangent line, a formula that we can use. And I'm going to express a couple different ways that we could refer to the slope of the tangent line as well. So for a lot of our examples in this section and in other sections we're going to get to, the slope of the secant line is also referred to as the average rate of change. Remember, slope really is just a rate of change. So the average rate of change. Or it could be called the average velocity, because velocity is really just a rate of change. So average velocity, but notice the word average shows up each time. And then that was just this red part right over here, which is just your y2 minus y1. So f of x minus f of a over the change in x's here. Relating it back to the difference quotient, we could just look at this as f of x plus h minus f of x all over h, where h is just what we're adding on to x to get to a. So if a is h units away from x, this is what we're looking at here. Or vice versa, if x is just h units away from a. But it's still ultimately the same thing. It's f of some value minus f of another value all over h would just be considered the distance between x and a. So the slope of the secant line has all of those meanings. If we address the slope of the tangent line now, you're going to see what word is going to change. It is no longer the average, it's something that we call the instantaneous. We want this rate of change at a specific instant. So this is the instantaneous rate of change. Or it is the instantaneous velocity. And then when we go to use a slope formula, we put the limit in front of it. So it's the limit as x approaches a of this formula. Or if we use the bottom formula, that h we eventually want it to go away. And as x approaches a, if it becomes an a minus a is 0. So in this case, if we use the h, that h will turn into a 0. And we're going to see further examples of it in the future lessons as well. So it could be the limit as h approaches 0 of f of x plus h minus f of x all over h. So we're going to go through a series of examples here. Now for these examples, most of them, we are going to need a calculator. If I were to test or quiz you on any of these, I'll make the numbers easy enough so you won't need a calculator. But the whole idea is just to go through this experience of using a table and going the long way just to see how slopes of secant lines get closer and closer to slopes of tangent lines, how we can use them that way. So for our first example, we're going to find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. So go ahead and pause the video, copy this down, and we want to make a hand sketch of the graph of y equals x squared and the point 1, 1. All right, so I'm actually going to draw this a little bit larger. I'm actually going to count every 2 squares are going to be 1. Okay, so when I go to graph, 0, 0 is the vertex of this, over 1, up 1, over 2, up 4. So we have our parabola here. And this is y equals x squared. So here's our point 1, 1. And what I'm going to do, because we don't know how else to find the equation of the tangent line, the slope of the tangent line, we're going to use a secant line. So what we're going to do is we're going to approach 1 from both sides, from the left of it and from the right of it. We're going to make tables here. So I'm going to make a table of my x value, my y value, and then my slope between the 2 points here. All right, so what I'm going to pick, I'm going to start just at, coming from the left here, I'm going to start at 0. Then I want to jump to get a little bit closer, so we could do a 0.5. I don't want to go straight to a 1. I want to maybe do a 0.9, and then we can do a 0.99, and then a 0.999. So like I said, we're going to get ready for our calculator here. We have to square all of these values, so go ahead and take your time, type these in, and we want to square them. So 0 squared is going to be 0. 0.5 squared is 0.25. 0.9 squared is 0.81. 0.99 squared is 0.9801. And 0.999 squared is 0.998001. Now what we want to do is find the slope. So we do the change in y's over the change in x's. So this becomes the slope of line PQ. So this is our point P again, and all of these are our Q values. So we're always taking the slope of line PQ. So this could be like our Q1, our Q2, Q3. So we always base these back off of our point 1, 1. So here, I could start with point P first since we're going to the left. So then this would become 1 minus 0 over 1 minus 0. So the first slope is just going to be 1. Then I want to do 1 minus 0.25 over 1 minus 0.5. So again, take your time, type that into the calculator. So we want 1 minus 0.25 over 1 minus 0.5. And then we get a 1.5 here. So we want to continue throughout. So the third, I know my values are getting close together here, but the next one we want 1 minus 0.81 over 1 minus 0.9. We'll get that slope. The fourth one will have 1 minus 0.9801 over 1 minus 0.99. And then the last one here, we'll get 1 minus 0.998001 over 1 minus 0.999. Let's go ahead and pause the video and get the rest of those values. Okay, so hopefully you guys were coming up with the following values. If you're not done yet, go ahead and pause the video at this time. But we were getting it jumps from 1 to 1.5, because look at how much closer we jumped. We were one whole unit away from 0, then we moved closer, then we moved extremely close. So these last few values should be extremely close. So we have a 1.9, 1.99, and 1.999. So the way we're going to write this, as x approaches 1 from the left, the notation here is 1 from the left becomes 1 to a little negative sign in the upper right corner there, kind of like as an exponent. So as x approaches 1 from the left, the slope of the secant line, so the slope of line PQ, approaches, we're going from 1 to 1.5, so it looks like it's getting pretty close to 2. So that's what we're looking at as x approaches 1 from the left. Next, we're going to make a table of values and do the same thing, but approach x from the right. right, so if we're approaching x from the right, we're getting smaller. So maybe I could start with a 2 and then jump down to a 1.5, knowing that I want to get a little closer. So maybe do a 1.1 and then a 1.01 and then maybe a 1.001. So squaring all of these, we're going to get a 4. If I square 1.5, we'll get 2.25. Square 1.1, we get 1.21. Square 1.01, we get 1.0201. And again, I'm squaring these because the function is y equals x squared. And then if I square the last x value, this will become a 1.002001. So I can call this Q6, Q7, Q8, Q9, and Q10. So again, I want to base this off of our point P, which is 1, 1. So here the slope would become, since I'm going to the right, I'll take the Q points and I'll subtract them here. So we'll get 4 minus 1. I'll subtract P from the Q points over 2 minus 1. So here I get a slope of 3 over 1. Next, we're going to do 2.25 minus 1 over 1.5 minus 1 and continue. The third one we'll do 1.21 minus 1 over 1.1 minus 1. The fourth here, or Q9, will become 1.0201 minus 1 over 1.01 minus 1. And then the last will become 1.002001 minus 1 over 1.001 minus 1. So go ahead and pause the video and just calculate those slopes and then continue playing to generate the rest of these answers. All right, so the following slopes, we go from a 3 down to a 2.5, and we jump down to a 2.1, and we get a 2.01, and a 2.001, and the more zeros we just add in between the decimal point and the 1, we'll just add more zeros in between here. So we could see as we approach, as x approaches 1 from the right, that's what this notation looks like. We'll put a plus sign up there to indicate that we're approaching a value from the right. The slope of our line PQ approaches 2. And they're just getting smaller. The slopes are getting smaller as we're approaching 1 from the right, and they're getting larger as we approach from the left. So all this is saying is we have a series of secant lines from some random point Q's that we're starting at here. So this is what's happening. If my screen could stay. All right, so first we started with a secant line here, and that wasn't close enough. So then we wanted to go here. And then we just keep getting close enough so we could see that our slope might be approaching 2. As we approached from the right, we started out maybe right here. And we kept getting closer and closer. I know it looks like a mess right now, but we could see that how the slopes of the tangent lines are changing. But that's what we did, and we just had to pick different x values, and we still kept going back to find the slope between each point Q and our original point that we wanted to find the slope of our tangent line. So it is a process. It is very time consuming, which is why we don't want to keep doing it. But in this section, we are going to continue to do this, and eventually we'll get away from it and learn a lot more shortcuts that will make the whole process a little bit easier. So we found the slope. So I'm just going to start a new page here with this. So the slope of our tangent line is 2. We want to find the equation now. I'm going to abbreviate equation like this. So we know our tangent line is going to pass through the point P, 1, 1, and we have the slope. So all we have to do is use y equals mx plus b, or we could use point slope form. Y minus y1 equals m times x minus x1. Either way, we'll get to the equation of the tangent line. So here we could say 1 equals 2 times 1 plus b. So 1 equals 2 plus b, and b would equal negative 1. So the equation of our tangent line is y equals 2x minus 1. Or over here, we could use y minus 1 equals 2 times x minus 1, distribute the 2, and then add 1. We get y equals 2x minus 1. So the equation of the tangent line is y equals 2x minus 1. So essentially that was what the calculator was doing. We can go into a table feature in there, but it was just kind of calculating points very close and seeing what the limit was as that x approached that special point here, or the x value here of 1. All right, so these are the 3 terms so far that we're going to first get introduced to that relate to physics. So as I mentioned before, an average rate of change, the whole phrase rate of change, stands for velocity. So velocity is the rate of change of what, though? It is the rate of change at which an object changes position. So the rate of change at which an object changes position. Velocity tells us speed with direction. And we're going to we'll get into this more a little bit later. But if we have a negative velocity, that just indicates that an object is moving backwards or to the left or down. If the velocity is positive, that just means the object is moving up or to the right or forward. Speed is the velocity without the direction, so it's just the absolute value of velocity. It's saying we don't care what direction the object is traveling, we just want to know how fast it's going. And displacement is just the change in position. What is the final position compared to the initial position? So let's say an object moved forward 5 feet, moved backwards 6 feet, and then moved forward another 3 feet. Because it kind of went back over its initial position, that doesn't even matter. We just want to know, it could travel back and forth or walk around in circles. At the end, we just want to know how far away is the object from where it first started. So it is just the overall change in position of an object. Something else we're going to look at later in this course is total distance traveled, and that's where we would kind of like tracking your steps on a Fitbit. We just want to know if you did walk 5 steps in one direction, 6 steps in the other, you walked 11 steps, but displacement would just be if you walked 5 steps in one direction and 6 steps back, you're just 1 step away from where you first started. But displacement tells us that. Total distance traveled is a different idea altogether. All right, so here is our second example. Please pause the video and write this down. So if you notice in this table, I do have a lot of values given here. And then these are the intervals. These are all the values of t. So first we're going from t equals 1 to t equals 3, which is up here. T equals 1 to t equals 2. So we're jumping from 3 to 1 and then 2 to 1. So that's kind of like as we're approaching 1 from the right. And then we get a little bit closer, 1 to 1.5. So these are not ordered pairs. These are just intervals for the values of t, kind of like a domain. And then we go from 1 to 1.5. Now that's not given in the table, so I did give you these off to the side. Problems like this on WebAssign will also give you that. They may not show up in the table, but they have to be given somewhere else. So this would be the ordered pair for at t equals 1.5, the distance would be 4.7 feet. At t equals 1.3 seconds, the distance is 3.6 feet, and then 1.1 is 2.5. So what we just essentially have to do is find all of these slopes. So we're first just going to show from our time interval of 1 to 3, write that off to the side here. I'll just say the slope of our secant line. So I want to go up here to the y values, which is distance. So these are like my f of t or d of t in this case. So I want to start with 15, and then from the 1 is going to be 2. So this becomes 15 minus 2, because these are the points I'm looking at here. We have 3, 15, and then we have 1, 2. So I want to find the slope of the line that goes through these 2 points. So 15 minus 2 over 3 minus 1. So that gives me 13 over 2, which is 6.5, and then this would be given to us in feet per second. So next I want to find the slope of the secant line here that goes from t equals 1 to t equals 2. So the slope of my secant line. So when t is 2, my distance is 8. So we'll get an 8 minus when t is 1. So the 2 and the 1 at the very end, those are going to stay the same. So 8 minus 2 over 2 minus 1 in this case. So this just gives me 6 over 1, or 6 feet per second. Now here we're going to go from 1 to 1.5, so I had that listed off to the side here. We have 1.5 and 4.7. So the slope of our secant line is going to become 1.5 minus 2 over, I'm sorry, that should be 4.7. That's our y value. 4.7 minus 2 over 1.5 minus 1. Now this is what you can use your calculator for. So if you do that, we should end up with a 5.4 feet per second. So if you notice, we're going 6.56. We're slowly decreasing. So we're going to keep getting closer and closer to 1. I started 2 units away from 1, jumped down from 1, and then 1.5, or 0.5 units away from 1. So next we'll do 1 to 1.3. So when t is 1.3, our distance is 3.6. So we do 3.6 minus 2 over 1.3 minus 1. If you go ahead and calculate that, you should get a 5.3 repeating. So we could just round it, 5.3 feet per second. So now these aren't decreasing as drastically. And then we'll do the 1.1 here. So the slope of our secant line here, again, when t is 1.1, the distance is 2.5. So we'll show 2.5 minus 2 over 1.1 minus 1. Go ahead and calculate this, but it should give us a 5 feet per second. So we kept estimating or approximating the slopes of the secant lines as our second x value got closer and closer to the first x value. Now, if we kept doing this and maybe went with a 1.01, again, we don't have that listed for us, but that would just be even better. And then we could answer this question. So estimate the instantaneous velocity at t equals. And that typically is just that last value we got because we are getting closer and closer here. So it is a good approximation. Now it might have dropped a little bit below the closer we get, but again, we're just estimating. So the instantaneous velocity, I'm just going to abbreviate, we could say is 5 feet per second at t equals 1 second. So again, this is the whole point. We go through that lengthy process, very time-consuming process, I understand, to eventually get to this, but we have to do it a series of times to see what the values are getting closer and closer to. All right, here's another similar problem. Go ahead and pause the video to write this down. Okay, so this question is a little different. It says, let P be the ordered pair 2, 2.1. So we're looking at this point right here as point P. We want to find the slopes of the secant lines PQ when Q is the point on the graph starting at x equals 0. So we could call this point here, call it Q1, call the next one Q2, over here Q3. We don't include point P because we're trying to find the slopes of the secant lines from each of the other points back to point P. Over here we can call this Q4. And then last we can call this Q5. So all of these are going to go back to point P. We want to find all of those slopes. So go ahead and take your time. So I'm just going to write this out as the slope from, let's say, PQ1. So then this will become, since P is to the right of this, I'll just go ahead and write this out as 2.1 minus 3.4 over 2 minus 0. Next we'll have the slope from P to Q2. So this will become 2.1 minus 3 over 2 minus 1, and then so on. So going from P to Q3. Now Q3 is to the right of it, so I'll just put that first. It really doesn't matter the order again. We could have 2.3 minus 2.1 over 3 minus 2. And we have the slope from P to Q4. That'll become 3.1 minus 2.1 over 4 minus 2. And then last we have the slope from P to Q5. So that'll become 3.2 minus 2.1 over 5 minus 2. So go ahead and pause the video and calculate all of these. Now, it could be a little bit misleading at first, but that's okay because we're still maybe a little bit far away. Slopes can fluctuate, but they should still all be relatively close to each other on this, if we're looking on one side. So if we go to calculate this first one, you should be getting a negative 0.65. And then the second one would be a negative 0.9. So it does look like one dips below the other, but as soon as we come to the third one here, now we're back up to the positive because we switched sides. So if we wanted to plot these points and kind of draw a curve between it, we would understand it better. But this is just to show you we're not approaching point P just from one side or getting closer and closer to that too. We're just looking at it from all these different points, and then we're going to compare them at the end. Looking at the slope from P to Q4, we should be getting a 0.5, which isn't that far off from 0.2. And then the last one, we should be getting, say, a 0.36 or 7, 6 repeating, I think it was. So we'll just put a 0.37 here. So all of these are in the same vicinity, but we're not approaching anything, like our x values are not approaching the 2, so we can't answer it like we just did the last question. But here we just found all the different slopes of the secant lines. So to answer this one, if we wanted to find the instantaneous velocity, we approached it a little different. So when x equals 2, what we can do is, because we weren't approaching from both sides, what we do is we just take Q2 here and then Q3, so just the slopes of the secant lines on either side of P, and we take the average. So just to write this out, again, we are not approaching x equals 2 from just one side. So we average the slopes when, in this case, x is equal to 1 and then 3. Or we find the slopes of those two lines and we can just average those together. So our instantaneous velocity, so we have the slope of Q2 and Q3. So Q2 was a negative 0.9, Q3 was a 0.2. So we take the negative 0.9 plus 0.2, this will give us a negative 0.7, and then we average that, so this will just all be over 2, all over 2, and we get a negative 0.35 for an approximation or an estimate of the instantaneous velocity at x equals 2. All right, in example 4, this is a lot like a previous example, not the one that we just did. Here we're asked, or we're told, if an arrow is shot upward on the moon with a velocity of 58 meters per second, its height in meters after t seconds is given by h is equal to 58t minus 0.83 t squared. So this one differs a little bit because we're given a function. We're not given a table anymore. And again, the wording could be a little different. They could give us the intervals, or here we have to create our own intervals. But if you kind of notice here, we're kind of centered around the 2. So it's not like we're going to 2 different sides and finding all these different slopes of the secant lines. We're still approaching the t equals 2 here. So we want to find the average velocity for the time period beginning when t equals 2 and lasting 1 second. So that means we have to create our own time intervals. So if our first one starts at 2 and it lasts 1 second, then we're going from 2 to 3, not from 1 to 2 or 2 to 1, but it's lasting 1 second. So then the next one we would go 2 to 2.5, 2 to 2.1, 2 to 2.01. So we could see that we're getting closer and closer to 2 with those second values of t. So these would be our time intervals here, 2 to 2.5. And then we have to use the function to find the y values. So next it would be 2 to 2.1, 2 to 2.01, and then lastly 2 to 2.001. Now part B again will ask us for the instantaneous velocity, and then that we can gather from the answers that we're looking at here. But you definitely need to have your calculators with you. So we're looking at 58t minus 0.83 t squared. So what we first want to do is determine this when t is 3 first. So I'm just going to say the average, abbreviate this here, velocity. So first what I want to do is substitute 3 into this equation. So just go ahead and do that on your calculator. Pause the video while you do that, and then just double check your answers with me. Now depending on how you round, I like to just show whatever is on my screen. So here I was getting a 166.53. Next we want to figure out this expression up here when t equals 2, and then that's what we'll subtract. So go ahead and do that. Pause the video. For this, you should be getting a 112.68. And then over the difference in our t value, so it's just 3 minus 2. So if you were not getting those numbers, try to recalculate it. Again, the 166.53 is just what we get when we do 58 times 3 minus 0.83 times 3 squared. The 112.68 is what we get when we substitute a 2 in, 58 times 2 minus 0.83 times 2 squared. And then these are just the difference in the t values. Again, pause the video if you need to get that calculation, and we should be getting a positive 53.85. This is given to us in meters and seconds, so we're going to have meters per second here. And since velocity is a rate, like how fast, like miles per hour, we always want meters per second here. So next what we're going to take a look at, the average velocity. Now the 2's are always going to be here, so my last two numbers I subtract will always be the 112.68 and then the 2. It's just these first two numbers will be different, so all we have to really do is calculate the newest number that's here. So right now go ahead in your calculator, type in the 58 times 2.5 minus 0.83 times 2.5 squared. Pause the video as you do that. And you should be getting, this one I'm going to carry out a little further based on what my calculator showed, but as long as you're close enough, 139.8125, and then we'll subtract the 112.68, and then this will just be over 2.5 minus 2. So pause the video again as you find this average velocity. And for this, it's still very close, but we're showing that we're increasing. Should be a 54.265 meters per second. And the process continues. So here, the average velocity, if you substitute a 2.1 into that equation, pause the video as you do that, you should be getting 118.1397 minus the 112.68. over 2.1 minus 2. Pause the video again to calculate this. And we should be increasing a little more to a 54.597. And again, because look at the jump. We jumped a half and then we just went 0.4, so it is decreasing a little differently. And then here, we'll do the same thing, very similar. So 2.01 is what we want to type into that function. Again, pause the video as you do that. And you should get 113.22672 minus the 112.68. And this time over 2.01 minus 2. Again, pause the video as you calculate this. And here we're getting a 54.6717. Both of these should be meters per second. And we'll do this one more time. Okay, here we want to evaluate that function at t equals 2.001. Pause the video as you do that. If you notice, the value at 2.001 is very close to the value at 2 because 2.001 is very close to 2. So we're getting a 112.73468 minus 112.68 over 2.001 minus 2. Pause the video as you calculate this. And it's not much higher than the last average velocity that we were getting, a 54.679 meters per second. So it's safe to say that we can leave it at that 54.67. It started to increase a little more, so maybe we could just, depending on how WebAssign asks you to do this, the rounding may be off a little bit. If you are typing some values in and they're marking them as incorrect, please let me know. Sometimes there's issues with WebAssign and how they want you to round. So you could be at the right answer. You may just not be typing in enough decimal places or maybe too many. But here, to answer this now, we could say the instantaneous velocity at t equals 2. We could just say is maybe a 54.7. The closer we get, we could maybe round that up. 54.7 meters per second. All right, and then we just have one more example to take a look at. This one does involve a trig function, so it's just to get us familiar, again, working with a trig function. But go ahead and pause the video and write this down. Okay, so this one is very similar to the last one. However, if you're going to use your calculator, make sure you're in radian mode. We are going to need it because a lot of these values are not going to be easy to calculate. Just the very first one will be, but all these others we are going to type into our calculator. So this is the function we're using. T is the time in seconds, and S is the displacement of the particle, the position there. It's in centimeters. So our velocity answers are going to, the unit of measure here is just going to be centimeters per second rather. All right, so first what we want to do is calculate this from the interval from 1 to 2. So if we look at from 1 to 2, first we need to figure out, this is what we're going to type in, sine of the t is now 2, so 2 pi plus cosine of 2 pi, and then it's minus, and we'll have sine of 1 pi plus cosine of 1 pi. Now, because all these first numbers are 1, all we have to do is the second part just once. And then this is over 2 minus 1. Well, this we can figure out if you just think back to the unit circle. Sine of 2 pi is 0. Cosine of 2 pi is 1. Sine of pi is, again, 0, but cosine of pi is negative 1. And then we'll get a 1 at the denominator here. So this becomes 1 minus 1, which is 2. 2 over 1 is 2 centimeters per second. Now, if you have a graphing calculator, you can just go back up and maybe edit this. So click on that again if it can recopy it. If you have an Inspire calculator, that's a lot easier to do on that. If not, we're now just going to go from 1 to 1.1. So really all we have to do is calculate sine of 1.1 pi. This is what you want to type in on the calculator, plus cosine of 1.1 pi. Now we know sine of pi is 0, cosine of pi is a negative 1, so minus a negative 1 will always turn into a plus 1. And then at the bottom we have 1.1 minus 1. So all we have to do is carefully type this in. Go ahead and do that. And then you can check to see what you get. Pause the video if you need to. But it should be coming up a negative 2.6007 centimeters per second. And yes, we did jump from a positive 2 down to past a negative 2. But let's just see what it is with the next one because we're closer to 1 now than we were at 2. So if we go from 1 to 1.01, here we just want sine of 1.01 pi plus cosine of 1.01 pi. Again, at the end, we'll get a plus 1. Now, if it helps, if we just did 1.1 minus 1, it's just a 0.1. So 1.01 minus 1 is a 0.01. It might make the calculations go by a little quicker. Go ahead, pause the video and calculate that. I'm going to write the others up here. And again, we're looking at average velocity. That's what all of these values are that we're finding. And then this difference in our denominator would be a 0.001. And then last we'll have from 1 to 1.0001. Again, pause the video if you need to. But from the interval from 1 to 1.01, we should be getting a negative 3.092, It still makes sense. We're just decreasing a little bit more here. From 1 to 1.001, this should be giving us a negative 3.137. And again, these are centimeters per second. And then the very last one is very close to the previous one here. It's a negative 3.14 centimeters per second. And since that's what it's approaching here, that's what we could use to answer part B. Estimate the instantaneous velocity of the particle at t equals 1 second. So the instantaneous velocity at t equals 1 second is a negative 3.14 centimeters per second. Okay, so in this section, as I've mentioned before, this was a lengthy process, but the whole idea was to show us how we can estimate the slope of a tangent line by looking at how the x values can approach a certain x value or point P that we're looking at from one side, that we could use the slope of the secant line to help us estimate the slope of the tangent line. As always, guys, let me know if you have any questions.